New Zealand is one of the founding signatories to the Antarctic Treaty. But more importantly, I think New Zealand always has a really strong relationship with Antarctica in that sense of kaitiakitanga, manakitanga, of that very special place. We want to see Antarctica preserved for the future, not only for its beauty and remoteness and special value, but also humanity depends on it.
A central theme of nearly all the work that we support in Antarctica is understanding change, in particular climate change and the impact on Antarctica and the Southern Ocean.
So the reason we are so interested in Antarctica is that it is one of the critical engines of the global climate system. So what happens in Antarctica will be felt around the world very, very quickly and everywhere. And this is really where the mandate for the platform came about, to think about how Antarctica will change in a warming world and what its global implications are of the response of Antarctica to that warming.
The rate of warming that we're seeing is really unprecedented in the geological record. Both the atmosphere and the oceans are warming. This means it's melting the ice sheets, it's melting the sea ice. This is impacting circulation, it's impacting biological activity, and it's really unlike anything that we've seen in the recent past that we've been able to observe.
The better the science we can do, the better we can make decisions. You can't manage what you don't monitor. So we want to understand what's happening in Antarctica to guide evidence and data-driven decision-making.
We've seen the loss of sea ice in the Arctic over several decades. And so the expectation was that we would also see loss of sea ice in the Antarctic. But the rate of change, how fast it is declining, is fairly sobering. When you understand the role that sea ice plays in our climate system and what the potential flow-on effects are, not just for the ecosystem, but for the whole physical system.
There's really core things that happen in Antarctica that keep the oceans working the way they do. The freezing and thawing of sea ice is like a heartbeat of the planet.
Antarctica is about 50 times the size of New Zealand. Sea ice is an apron of ice that forms from the ocean around Antarctica. Essentially, when the winter comes, the surface of the ocean starts to freeze. And then over the next few months, it will freeze to a thickness of between 1 and 2 metres over an area that essentially doubles the size of Antarctica itself.
You take the sea ice away, then the front of the ice shelves and the ice on the continent around the coast is exposed to waves, to extra heating, solar radiation, you name it. It's sort of out there all of a sudden, whereas it was quite protected when there was a layer of sea ice in front of it. In the Ross Sea region, there are regular formation of polynyas. There are holes in the sea ice. So the formation of these polynya, which happens over days and weeks, can influence how strong the circulation in the deep ocean is over decades and centuries, actually.
Many of them can be quite small, tens of kilometres in scale, but it's where you're starting off this bottom water, but also growing sea ice.
We've been monitoring the outflow of dense water in a place that's very critical for the global ocean. When we talk about ocean flux, we just mean the movement of water, the exchange of water across the Ross Sea shelf. So that exchange of water is changing the heat and the salts, the nutrients and the gases that are on the shelf and in the deep ocean. So that's why it's a critical part of understanding what's going to happen to the Ross Sea and also what's going to happen to our global ocean. Another big achievement of the program is to put in Argo floats so that we can see how the density on the shelf is evolving with time.
There's all sorts of flavours of Argo, but it's essentially sending out robots, thousands of robots throughout the oceans, and they bring in this subsurface structure every sort of 10 or so days. And it's been one of the hidden sort of secrets to why our sort of weather forecasting models are doing so much better.
The significance of the Southern Ocean in general for global climate is also that it is primary sink for CO2, for greenhouse gases, which we emit into the atmosphere. So we need to keep the circulation in the Southern Ocean going. Otherwise, we risk that the Southern Ocean would actually reduce its capacity to uptake that additional greenhouse gas.
I think everybody knows that we're burning fossil fuels and putting carbon dioxide into the atmosphere, and that's the main cause of the global warming. What actually most people don't know is of that carbon dioxide that we put into the atmosphere from burning fossil fuels, only about half of it stays there, and the other half is going into the oceans and into the biosphere. The Southern Ocean has taken up about 10% of all of the CO2 that humans have produced over the last couple of 100 years.
There's also biological uptake of CO2, especially around the sea ice edge. That's where phytoplankton, these are photosynthesizing algae. They take up carbon from the atmosphere, turn it into organic matter, and some of that organic matter eventually sinks through the water column and makes its way to the seafloor, where it's isolated from the atmosphere. My hope is that we're able to get a better representation of sea ice, because that's crucial for carbon exchange and for the processes around the Southern Ocean.
So the sea ice provides this very large area that supports the very base of the food chain.
What we're investigating here is the potential that platelet ice plays quite a significant role in supporting the base of the food chain for the Ross Sea ecosystem.
I like to think of it as the autumn leaves of the ocean.
And they float up to land against the base of the sea ice. You think of the sea ice as the roof of the ocean. And so what we're trying to do here today is core through this delicate structure. If you imagine trying to core through autumn leaves and keep their structure in place, that's a good illustration of what we're trying to do.
Any changes at all to how it forms, so that means what time of the season it forms, all of those are likely to have impacts on the marine food web.
Oh, lovely platelets, yes. Thank you.
When you talk about benthic, that basically means anything that lives on or in or associated with the seafloor. Things like sea stars and sea urchin and fish that might feed on the seafloor can be considered benthic too. 50 to 60% of the animals that we find on the seafloor you don't find anywhere else in the world. What we have done in our field campaigns, we've made holes in the sea ice and then we put a remotely operated vehicle down and use that to video transects of the seafloor across lots of different depths and at lots of different places. And we can also use those remotely operated vehicles to actually collect specimens.
We have a lot of knowledge about the Ross Sea ecosystems, but over the years a lot of that information has come from divers, which has been quite restricted to depths shallower than 40 metres or so. As we've been able to do these coastal surveys, we've actually seen really dense communities of seaweeds clearly attached, clearly living, and extracting light from the environment. And we were shocked to see how deep some of these communities were living and how dense they were in these environments. And it really changed our perspective on the spatial area that these species are covering and the potential contribution they have to the fixation and storage of carbon in these cold environments. So warming doesn't just mean temperature, it means more fresh water, it means more sediments running off the land. Those changes could mean that there could be an increase in photosynthesis of phytoplankton. That might increase carbon storage. It might mean that we get less of it. It might mean that the benthic communities are getting less food. It might mean that they're getting more. And all of those things, we see positives in one place and negatives in another. And the balance of how that's going to impact our environment, we don't really understand yet, but we know that in a 2-degree world, that's going to be different.
We always used to talk about climate change as being something that was going to affect ecosystems. It's pretty clear now that, we're seeing big changes to the marine environment, and we're seeing changes to species and organisms in the food web because of that. We try and look at the system as a functioning whole. So we go from the physical oceanography, the environmental conditions that set the environment, and then we look at how that solar energy is taken up by phytoplankton, so the growth of the primary producers, they're the sort of base of the food web, and then how that energy and organic matter is passed up through the food web. So through the small zooplankton, the grazers, into the larger zooplankton like krill, up into the small mesopelagic fish, the small 10-centimetre long fish living in the midwater column, and then up into the top predators like the seabirds, the penguins, the seals, for instance, and the whales. And also how that material sinks down through the water column to near the seabed. But recently, for the last 5 years, we've seen massive decreases in that sea ice. So it was picking up for reasons that are not particularly clear, and now it's kind of really decreasing fast. But there are going to be effects through the whole of the system. For something like an Antarctic fish, the effects of that changing sea ice are probably not going to be so dramatic, but they might be affected by changes to the deep currents or the way that food is distributed on the seabed. So they're going to be more subtle changes.
About 0.2% of Antarctica is actually ice-free. And this means that it also makes Antarctica one of the largest cold habitats in the world for organisms ranging from bacteria up to nematodes, springtails, mosses, and lichens. And these are the primary types of organisms we find in terrestrial ecosystems in Antarctica. As it is, it's one of the most unique ecosystems in the world. Everywhere we look, we see evidence of a long-term isolation from the rest of the planet.
Antarctica is a dry continent and it's a really extreme environment, and the lakes are the focal point of where life actually is really active and really dynamic. The lakes sit in what we call closed catchments, so water flows in, meltwater flows in during the summer, but no water flows out. There's no rivers flowing out of most of them. If you get a change in meltwater production, then the lake level tends to go up, and that's what's been going on for the last kind of 50 years or so at least. Changes in the structure of the lakes themselves and changes in the communities that can live in them.
As the continent warms up, it's intuitive that more water will become liquid. But where would this liquid water come from? And where is this liquid water going to go? Those are big questions.
Antarctica is home to massive bodies of ice called ice sheets. There's the East Antarctic ice sheet, which if all of it were to melt entirely, it would raise sea levels by over 50 meters. At present, the Antarctic ice sheet is losing up to 150 gigatons of ice per year. To put that in context, that's nearly 3 times Lake Taupo being added to the global ocean every year. So we're constantly raising sea level from changes in the Antarctic ice sheet. And so why this matters is currently we already have issues with coastal flooding during big storm events.
Climate is a synthesis of weather events. It usually describes the state of an environment under the influence of weather regimes. Our interest in Antarctic weather and climate is really understand how weather has been changing in the past and how it will change in the future, and how weather events might influence certain climate states in the future. So thinking about climate change, how particular extreme weather events, warming events happening in Antarctica could then translate into impacts on the ice environment, on the terrestrial environment, and the ecosystem. We collect our own observations, so we rely on climate and weather stations. We rely on specific field campaigns that collect surface temperature, soil moisture.
the atmosphere over the Southern Oceans. It's one of the windiest, most turbulent parts of the global climate system. How those storms and winds change over the Southern Ocean, that's a big part of the story of how the climate will evolve over New Zealand and other parts of the mid-latitudes of the Southern Hemisphere.
Antarctica is really clearly such a core component of how our planet operates, how our oceans work, how our atmosphere works, and all of that ice and all of that circulation of the ocean really drive the climate of our planet as we know it.
We now have seen the emergence of extreme climate events. We saw freshwater flooding on tops of ice shelves. We have seen breeding failures of emperor penguins, things that I think 20 years ago we just wouldn't have expected to see in our lifetimes. Another really important trend that we have observed during that time is the recent rise in mistrust of scientific expertise and expert advice. And I think this is a really worrisome development in a time when we need scientific insights more than ever.
But we're doing it because it's needed, because it has impact, because it matters to communities in Aotearoa, because it matters to communities in the Pacific. It matters to communities around the world.
What gives me hope is knowing that we're the ones causing the problem. We're doing all of this burning of fossil fuels and things. We have 100% of the power. We can turn off the tap whenever we choose to.